want to take a look at the total law of probability and Bayes rule. One thing that you have to note here is that the concept of total law of probability is essential to help us understand Bayes rule, okay? So before I use a scenario to explain the concept of total law of probability, let's take a look at the following theorem. Okay, so in this theorem, if a finite sequence of events from a partition of a sample space, okay, then for any event B defined a sample space such that we can express the probability of B in this form, which is going to be the sum of the multiplication rule technique, then we can say that this is the total probability rule for this event, okay? So in order to understand this better, let's take a look at this scenario. So we have a sample space here, and we have some event here, which is basically a partition sample space. And we know what a partition sample space means from our previous tutorial on the operations on event, okay? So a partition sample space is basically a collection of events that are disjoint or mutually exclusive. So if you look at the sample space, we have the event here, which seems to be disjoint or mutually exclusive, A1, A4, A3. You can say that these are disjoint or mutually exclusive. Now we have an event here B, which seems to be intersecting with this disjoint event, and this event is of interest to us. So now let's assume that this sample space is a city, okay? And this city has some area. So this is area 1, area 4, area 3, area 2, up to area 6, okay? We have other areas here. And we have some event here, which is of interest. So basically, let's assume that we are interested in the total number of COVID-19 cases in this city. So B is the event of obtaining or recording a COVID-19 case in this city, okay? Now, because this city is partitioned into areas, you are supposed to look at the areas, right? So for instance, if you take a look at area 1, there's a portion let's say there's the amount of COVID-19 cases that it has recorded. If you take a look at area 4, this is the portion of COVID-19 cases that it has recorded. The same applies to area 3, area 6, and other areas, okay? Some of the areas there was no record of COVID-19, okay? So we are interested in the probability of this event here. So how do we get this probability? So now to get this probability, basically you're supposed to get the probability for this area and then multiply it by the probability that you're going to record a COVID-19 case, given that it's coming from area 1. Then we also do the same for area 4. We get a probability for area 4. Then we multiply it by the probability that we're going to obtain or record a COVID-19 case, given that it is coming from area 4. Then we are going to add it to that of the probability for area 3, multiplied by the probability that we are going to record a COVID-19 case, given that it is coming from area 3. Okay, so this is basically the analogy behind the total of probability. So let's take a look at how to prove the theorem that we have here. Okay. All right. So now we have this expression. So we have the event B, and we know that this event B seems to be intersecting with a city. Okay, these are COVID-19 cases that we are interested in the city, which is a sample space. Here I'm using S for the notation. Okay. And we know that the sample space is a partition sample space, okay? So we can express this in this form, okay? Which is going to be the union of this event is similar to that of the sample space. We already know this from our previous tutorial, okay? All right. Now, when we apply the distributive law on this is what we're going to obtain, right? So we know the distributive law. Once we apply it on this, we obtain this one, okay? And based on what we have here, we can say that B intersection AI for I running from 1 to n are also mutually exclusive events, okay? So you can see that if we record a case in a particular area, there's no way we'll have the same observation in this area, okay? So this will also be mutually exclusive. All right. Now, once we take probability on both sides, so once we take probability on this side, on the left-hand side, as well as on the right-hand side, we obtain this because we are mutually exclusive, okay? All right. So once we apply the multiplication rule, we can also obtain this, okay? Once we apply the multiplication rule, we can obtain this. Then we can generalize this to obtain this, which is similar to the theorem that we just looked at, okay? So this is a proof for the theorem. All right, now let's take a look at some example. So in a certain assembly plant, three machines A and B and C make 30%, 45%, and 25% respectively of the product. It is known from past experience that 2% of the product made by machine A, 3% of the product made by machine B, and 2% of the product made by machine C are defective. So if a finished product is selected at random, what is the probability that it is defective? Okay, so we want to get this. So let's take a look at the solution. So first of all, let D denote the event that the finished product is defective. Okay, so we wish to find a probability that the finished product is going to be defective, but there's a condition here. If it is known from past experience that 2% of the product made by machine A, 3% of the products made by machine B, and 2% of the products made by machine C are defective. Okay, so in order to get this probability that the finished product is going to be defective, we can rewrite it in this form. So the probability that the finished product is defective, given that it's coming from machine A, multiply by the probability of machine A, then you're also supposed to add it to the probability that the finished product is defective, but it's coming from machine B, multiplied by the probability of machine B. Then I'm going to add it to the probability that the finished product is defective, but it is coming from machine C, multiplied by the probability of machine C. Okay, so once we obtain this, we already know the probability for this. There's a probability that the finished product is defective, given that it's coming from machine A, and there's a probability of machine A. You also get that for machine B, right? And that's a probability for machine B. The same applies to machine C and the probability of machine C. So once you use a calculator to compute this, you obtain this result. Okay. So this is going to be the solution for this question. Very simple. Let's take a look at another example. Okay. So before that, let's take a look at the base rule now, or the base theorem. Okay. So the base theorem actually is based on the total of probability. Okay, so once we know what the total of probability is, now we can take a look at the base theorem or the base rule. So let's A1, A2 running up to AN be a collection of events which partition a sample space. Let B denote an event defined on a sample space that the probability of B is not equal to 0. Then for any of the events AJ, J running from 1 to n, the probability of AJ giving B can be expressed in this form. So, okay, can express as a probability of A intersection AJ intersection B divided by probability of B, and using the multiplication rule, we can have the numerator expressed in this form, and the denominator is now expressed in this form. Okay, that's the total of probability. Okay, so what does this mean? So let me use the COVID-19 case scenario. So let's assume that this is going to be the probability that the JIP area recalls COVID-19 case, given that we know the total number of COVID-19 case. Okay, so that's basically how the base rule or theorem works. It is based on the assumption of the total of probability. Okay, once we know that, we can work with the base rule. All right, so now let's take an example. So a consulting firm rent cars from 3 agencies, 30% from A, 20% from agency B, and 50% from agency C. 15% of the cars from A, 10% of the cars from B, and 6% of the cars from C have bad tires. If a car rented by the firm has bad tires, we want to find the probability that it came from agency C, right? So let's take a look at the solution. So first of all, let T denote the event that a car rented by the firm has bad tires, okay? And we wish to find the probability that the car is coming from agency C, and that given that it has a bad tire. Okay, so first of all, we don't know the probability that a car rented by the firm has bad tire, so we have to get that probability. Okay, and that probability is conditioned, because if you look at the question, 15% of the cars from A, 10% of the cars from B, and 6% of the cars from C have bad tires. Okay, so to get a probability that a car rented by the firm has bad tires, we can basically from this we can express this in this form, which is quite okay. And using the multiplication rule, the numerator can be expressed in this form. But if you look at the denominator, this is how it's going to look like. So this is going to be a probability that a car rented by the friend has bad tire, given that it's coming from agency A, multiplied by the probability of agency A. We are going to add this to the probability that a car rented by the friend has bad tires, given that it's coming from agency B, multiplied by the probability of that agency B. Then we're going to add it to the probability that the car rented by the friend has bad tires, and this time it's coming from agency C multiplied by the probability of agency C. So that's going to be this how you're going to express the probability that a car rented by the friend has bad tires, because there's a condition to it. Okay, and we know that numerator can be expressed in this form using the multiplication rule. Okay, so for that. All right, so now let's take a look at the solution. So there's going to be the probability that a car rented by the firm has bad times coming from agency C multiplied by the probability of that agency. Then we're going to divide it by the probability that a car rented by the firm has bad times, which has this condition. So there's a probability that a car rented by the firm has bad times and it's coming from agency A multiplied by the probability of agency A. There is a probability that a car rented by the firm has bad times and it's coming from agency B multiplied by the probability of agency B, and this time this one is for C. So once you use your calculator to compute this, you obtain this result, okay, which is quite simple to compute. Okay, all right, so this is going to be a trial question. I'm going to leave the solution in the description of this video so you can check it out. Please don't forget to subscribe if you have not, and thank you for watching.